work today that I'm going to talk about is done by Medegarda and myself and two postdocs, Shi Wu and Schaffer, who have done a lot of the work on the transient absorption and a lot of collaborations with different experimentalists doing this. And I want to call out Phil because we started thinking about this while we were on sabbatical visiting Phil. I realized I had forgotten this, and you might really not know where Louisiana is. You've probably heard of Louisiana at some point, and when you think of it, you think that it's sort of an exotic locale, sort of very special scenery, and that turns out to be exactly true. It is a very, very special looking place. It's somewhere near my house, actually. So you should visit sometime if you can. So what I'm going to talk about is this using, trying to do strong field physics using attosecond pulses and precisely synchronized lasers. So I'm going to look at, again, having an attosecond XUV pulse and the synchronized laser field, and doing these coupled solutions to try and actually learn something, but also get close to connection to experiments. And we've done collaborations with 3 different experimental groups over the last few years getting results on this. Steve Leone's group in Berkeley, Ursula Keller in ETH, and Giuseppe Sansoni in Milan. And then we've also had a collaboration on macroscopic reshaping of attosecond radiation with Arvinder Sandhu, who is local. Is he here today? He was here the other night. He's at the University of
He's coming. He's coming.
Okay. He's coming. Well, you tell him I mentioned it. I did my duty.
There's the video.
So, well, it's impressive if he's coming up today. So the idea here is that the attosecond pulse, which is short, a few hundred attoseconds long, is precisely synchronized to somewhere within the IR laser pulse, which is maybe, this one is about 7 femtoseconds long. So again, the half period of the IR laser is about 1,300 attoseconds. So this is a small fraction of that and a small fraction of the overall period. And again, the idea is that some infrared laser pulse got split in half. Half of it went off to make harmonics, which by the tortuous process we discussed, or one of the tortuous processes that we've discussed over the past few days, is made into an XUV pump, either a single pulse or a train. And that is used to pump some sample, and the rest of the IR pulse is used as a probe, and there's a delay that can be controlled. And so the idea of any transient absorption is to try and characterize the polarization that can be made transiently in a medium by a pump pulse. So the idea is you kick something, you dump some energy into some system, and then you want to come along later and see. A basic question would be, is the energy still where I put it? Like, has it decayed? Has the system returned to its ground state? Stuff like this. Those are not exactly the questions we'll ask in these studies, but that's the general idea, is that you can study transient polarizations that you induce by pumping a system. And it's, by definition, these excitations are not going to last forever. So we look at it as a function of delay, you get some idea of what's going on. And so here's sort of the really basic idea. The idea is that I would have these 2 pulses, and they have some delay between them. So here's the IR pulse now, and I don't have the little wiggles. And here's the attosecond pulse. And I pass this through my material. And on the back end, I have a spectrometer, and I look at how much light got transmitted through it. And assuming I had, for instance, initially a smooth frequency distribution in my pump pulse, some frequencies are missing here. So some light has been absorbed. And if I look at the difference of what I put in and what I took out, then I get an absorption signal. And so the idea is, here's one delay, and here's one absorption spectrum. And here's a different delay, and here's a different absorption spectrum. Okay? And what you do is you put all of these together on a plot where delay is going this way and frequency is going this way. And one of these delays gives rise to a spectrum, which is a thin slice here. And then you do this. Then you do this at many, many different delays, and you build up a spectrogram. Yes?
Sorry, I'm confused. So is the IR the probe or the pump? Is the IR the probe or the pump? Sorry.
I don't know.
No.
As in, I don't actually have to know. So that's too quick an answer, but the spectrum of these two pulses don't overlap in any way. One is centered at about 1 eV, and one is centered at 20 to 100 eV. So it's very obvious that the XUV pulse is going to do the excitation out of the system, because we're going to keep the intensity of the IR laser low enough that it's not going to pump the system out of its ground state. So that would clearly say that the XUV is the pump and the IR is the probe. However, you could also take the view that, I mean, once the electron is excited, the IR pulse is going to do a lot to it. There's going to be many orders of nonlinearity around. So that looks kind of pumpish as well.
So why does the probe go first?
It doesn't have to.
Okay.
We're going to look at all of these, all of the possible delays. And so that's what's been done here, is all of the possible delays. This is a calculation that's actually done. I'll talk about it more or less throughout the whole talk. This is done for helium atoms, and the attosecond pulse is about 300 attoseconds long. It's the 7th attosecond pulse. But my point here is the thing that you get. This is the spectrogram. So let me push the button. Yes?
What's the absorption spectrum? It's in IR range or in the...
No, it will turn out that this is in the XUV region.
Oh, okay.
So we're going to look at how much of the XUV light gets absorbed or not. That's what we want to know. In principle, you could look at the IR, but you've got a lot of IR photons, and you don't want to be aiming them at your spectrometer. So, I mean, it would take filters and things. But this is dead simple, because the XUV pulse is not strong. So that's what we're going to look at. So what you get out of this is a spectrogram, which is a thing that you take by stitching together many, many different spectra taken at a set delay. Okay, so it's very important that we understand that the coordinate down here is delay, not time. Okay, and that means that the resolution that I see in my spectrum is going to be set by parameters of the system. In other words, how fast does the polarization decay, or if what's the gas pressure, what's the dephasing time, all sorts of things like this. It is not controlled by any kind of uncertainty principle. And that's because we measure the result of an entire experiment without knowing what happened at any given time.
In this schematic, what does the transient feature?
The transient would probably, in this, would refer to the fact that the features, the size of these features here, is directly tied to when the system was pumped with respect to when the IR pulse ends. So in other words, there are features here that are only there if the two pulses overlap. And in that sense, it's transient. But it's a very, very good question. So really, the central task is you have a transient absorption spectrum, and it encodes for you some ultra-fast dynamics. So this spectrogram encodes the dynamics in the system, but not in a way that's maybe completely obvious. Right? I mean, you can think of this as an encoder, and somebody has a decoder trying to do the experiment. Yeah. One more click. And so here's another way to think about what's going on. Is here is I've chosen a particular delay where the attosecond pulse comes along during the envelope of the IR pulse. Now, in the situation that we're talking about, the XUV pulse is going to start all of the dynamics. So there's nothing happening here because the IR pulse doesn't excite the system. But once it gets excited, then we have a very fast polarization response, because now we have something in a high-lying excited state, something in the ground state, right? and the two beating against each other will give you a very fast polarization, basically at the frequency difference between those two states. And so that's the very fast green stuff here. And also the IR pulse will induce linear or nonlinear processes between the excited states, and this will give rise to a slower modulation of the overall signal. So there's an underlying fast polarization signal, which just has to do with the fact that you've excited the system. And then we come along and we mess with that polarization. We amplitude modulate it by using the IR laser to couple it to other states in the system. And so here is really the picture you want to keep in mind. You've got the ground state. The excited states are sort of 10 eV or more away. It's the XUV pulse that does this excitation. Then you have excited states that are 1 eV or less apart, and the IR laser moves them around. So in these sorts of experiments where you keep the IR intensity moderate, and we discussed the other night how an IR intensity that can't excite the system can still look like a really strong field to the excited electron, right? It will find itself above the barrier and all sorts of things like that. So the XUV starts the time and the IR induces the dynamics. And so it's the IR-induced dynamics that we want to study this way. And so this is just like AM radio. You have a carrier signal, which is the fast polarization that was started by doing this excitation. And then you have a modulating signal from coupling these states together with the IR laser. And this gives rise to an overall polarization, which is very complicated. And this is, of course, what goes into Maxwell's equation. So this is something that we were kind of thinking about the other day, so I realized that we have this movie. So here's a very simple example of the kind of thing that goes on. So just consider 3 low-lying levels in helium. I've got the 1s, or I should say 1s squared state, the 2p state, and then I've got an IR laser that is tuned so it kind of couples the 2s and the 2p state. So all throughout this talk, I'm going to talk about bright and dark states. It's kind of a very dangerous thing to say in a room with quantum opticians because they have, I think, different meanings of dark states. But what I mean by a bright state is one that's accessible by the XUV laser from the ground state. So those are the kind of states you could see in synchrotron spectroscopy. You know, they're one photon. They have one photon matrix element to the ground state. So they're bright because they can be lit up by the XUV laser. The states like the 2s over here that are not directly coupled to the ground state, they're dark for me. They're dark because the XUV laser the XUV pulse can't light them up. So anyway, we have an XUV pulse and it's going to be here and it's going to excite some population in the 2p state. And then the IR pulse is going to come along and couple that to the 2s. And there's going to be a plot here of just the excited part of the wave function. And so as time goes along here, you see first we make this 2p state, then the IR pulse comes along and messes with it. And we're left with a superposition of 2s and 2p that's going to oscillate then forever after I show this again. So early on there's nothing. Then the XUV pulses come. At this delay, it makes just a 2p state. And then the IR pulse comes along and couples that 2p state to the 2s state rather strongly. And so then it can make a superposition of these two states. And it leaves the system in a superposition state. So like Tony was talking about yesterday in the calculations that Rob and Sandra had done where they started in a superposition of 2 different things. This would be one way to do it. But from the transient absorption point of view, what this combination of 2 states does is it leaves the system with a complicated time-dependent dipole moment. So now you can see it again. You see the initial wave packet gets made and then modulated and then left.
What is the lifetime of the 2p state? The spontaneous lifetime?
Excuse me?
What is the spontaneous lifetime of the 2p state?
Really long.
Okay.
And so the lifetimes and the line widths and all that stuff in the experiments and in the calculations are way, way shorter than those. Okay. So that's something we're going to discuss. What is absorption? Basically, if you get nothing else out of this talk, you're going to be able to at least parrot my answer to what is absorption, which is absorption is an interference process. Okay? So that's what we'll get to. So here's again our favorite slide where we talk about we can solve the one atom Schrodinger equation for we have some light field or fields here, right? This will be the combination of the IR and XUV lasers. This is, for instance, something that describes helium and far below the doubly excited states, so this is a one electron superpotential. You calculate a polarization by calculating the time-dependent dipole for the whole pulse, then Fourier transforming it, and that's your polarization. And then that's what goes into the space marching form of the Maxwell equation that we talked about that ignores the backward propagating light. So this is the praxial approximation for the light envelope. So what is absorption in time? You're probably used to thinking about absorption of light in terms of a cross-section, right? So the system will absorb this frequency. The system won't absorb that frequency, right? How does that happen, right? And one thing I want to say is it can't happen by photons, okay? Not for us, because we've got a bazillion photons, and we know that the Maxwell equation description of this system is essentially perfect, right? And so we have to be able to get absorption and emission, as we talked about the other day, out of this coupled equation treatment. So what is absorption in that picture? And so if you have a time-dependent picture of absorption, here's sort of how it looks. So again, let's just say, how does XUV light that is more or less resonant with this 1s2p transition, how does that get absorbed in a sample? Okay, how do I think about that? And in this treatment, single atoms alone by themselves don't absorb any light. All right, it takes all the atoms working together to actually absorb the macroscopic amount of energy from the pulse. So here's what happens, that when the XUV pulse comes in, there's no IR pulse now for a little while. The timing of the initial excitation is well defined because you have this really short XUV pulse. And so you start a dipole ringing at this frequency difference. So here's the dipole ringing with a period 2 pi over this resonant frequency. And this excitation is, in the approximation that there's nothing funny going on and these are just two normal bound states, this excitation is exactly out of phase with the driving field that made it. Okay? And that comes out of first order perturbation theory and the time-dependent Schrodinger equation, or however you want to do it. So this is ringing, ringing, ringing. It's out of phase with the field. So it's going to make a polarization that's going to contribute to a new generated field, which is out of phase with the field that made it. Right? And so now these two fields will be able to interfere destructively, and energy will disappear from the beam overall. Now, in this time domain picture, so we have here that the timing of the initial excitation is well defined. It's out of phase with the field that made it, so we have the possibility for destructive interference. But here's another wrinkle in this. To see absorption, we have to impose, nature or us or somebody, has to impose a time scale for decay or decoherence of this dipole ringing. In other words, it's got to run down over some amount of time. Otherwise, this rings forever, and the dipole Fourier transform of it will be a delta function. So all the energy will go into a frequency bin of 0 width. All right. So there's always something that provides a time scale, ultimately, for the system to lose this phase coherence. Okay. We do not need the population to go back to the ground state. That doesn't happen, doesn't need to happen. We just need this dipole to decohere so that the dipole response of the system goes to 0. And so then we get a frequency response with a finite width that can be seen in the spectrometer and can be calculated before the end of the universe. This time scale, it's independent of the pulse durations that you're putting in. That's the important part. It's an external time. So it is imposed by, at the very longest times, by spontaneous emission. In normal experiments, it's imposed by the gas pressure, the atoms running into each other, all sorts of effects. In our calculations, we impose it. We impose a window function on the dipole so that it eventually runs down. But we make sure that that time window is longer than all of the times that we're interested in the experiment, so that it would give features that are narrower than all the features that we see in the spectrogram, which are due to actual dynamics that we're interested in. So here's one way of thinking about how absorption happens in this picture. And I like this. I stole this from one of ours paper. So think about that. I have a very thin layer of gas, and I have some field going in that has a distribution of frequencies. And maybe the frequencies don't all arrive at exactly the same time. So this is a chirp. There's a very thin layer of atoms here laid out in a 2D array. And what do I see after the gas? Well, after the gas, I have the field that went in, and I also have a new field that got generated because I made a polarization in the medium. And the generated field, you can show, is proportional to the time derivative of this polarization. And so in the frequency domain, this time derivative introduces an I, factor of I, which is the pi over 2 phase shift that we need for the generated field to be out of phase with the field domain. So now if we look at the light that's coming out, let's just say, what is the spectral density? In other words, how much energy per unit frequency is there in the light coming out? Well, you would get that by multiplying some factors times the spectral amplitude of the pulse squared. So this would tell you roughly how much, not roughly, this would tell you up to a constant factor how much energy you had at each omega. Because the field that comes out is the linear superposition of what went in and what got made, it looks like this. There's 3 terms. Here's the energy per unit frequency that we put in. And here is an interference term between those 2 things. And out here is a field just due to the generation. This is like high harmonics. This is what we talked about the other day. This is a very low order process compared to this one in what we're doing, because we don't have enough intensity to make any high harmonics. So the only game in town is this interference term between the generated and the input field. And this can be either positive or negative. If it's negative, it's going to subtract energy at a given frequency. If it's positive, it could add energy at a given frequency. And the whole point of the kind of calculations that we're doing and thinking about is that the IR laser can redistribute the energy that the medium has gotten from the XUV laser over the bandwidth of the IR, and actually outside the bandwidth of the IR using nonlinear processes, but over the bandwidth of the XUV laser. So in other words, you have an XUV pulse that's, say, 5 eV broad, and then the IR pulse can do energy redistribution within that 5 eV envelope. Yes?
So is energy conserved here?
Yes. So the energy that comes in other words, the energy that goes into exciting the system and making this polarization will get pulled out of the field.
I know in reality that's true, but
In the calculation, yeah, the way that they're coupled.
Even though you put in by hand this artificial decay of the dipole?
Yeah, because that's not, so that's only going to determine how the energy is distributed in frequency, but not the absolute amount of it. And so my artificial decay, or the real decay in an experiment, and by the way, this sort of thing will come from the spectrometer resolution as well, right? So the spectrometer resolution is equivalent to, and so the resolution is often not that great, and so it can be equivalent to a few hundred femtoseconds damping time. But my point is that the features in the spectrum that the artificial window induces are narrower than all of the real features that we want to look at. So, and we're okay. But do you understand my answer? I'm not cheating, right? The window function is just determining sort of the width of the features, but not the absolute amount of what goes on. So it really is true that you can, the XUV goes through and it causes ionization, and that causes excitation, and that will pull energy out of the field downstream. You can see how that goes. So this is really, I mean, you either buy this or don't, but this is the interference term between the generated field and the input field. And this is what is going to add or subtract from what I put in. So again, there's always two time scales involved. So for instance, again, let's just think about this 1s2p absorption, right? There's the duration of the pulses that are driving the whole process. Then there's the duration of the calculation, or the resolution of the spectrometer used in the experiment, something, right? It's not always us. And so we wanted to have a finite duration. So what happens? So here, for instance, is the frequency spectrum of an input pulse, which is actually about 60 femtoseconds long, and sits on top of this 1s2p transition. And so the dotted line is the initial spectrum. And this thing with a hole in the middle of it is the spectrum that makes it through the gas after you're done doing the calculation. And so this looks like absorption, right? I mean, you lost energy right at the resonance there, all right? But notice a couple of things about this, not least of which is that if you have a long medium, and once you've absorbed all the energy there is at a certain frequency, you can't keep absorbing it, right? You do this in a coupled way, so you can't just keep pretending that the system, that more energy can be eaten. Now, this is not to say that we have saturated the absorption, all right? Most of the atoms in the gas are still in their ground state. It just means that we've used up all of the energy that we sent in at a given frequency range. And so then this will start to spread. All right? So this, yes?
Just to be clear, I mean, you don't have an IR pulse here. It's just the
I don't have an IR pulse. This is hard enough.
UV and the propagation
Yeah.
of the medium.
That's right. And this is already kind of messing with our head a little bit, right? Not pulse. I mean, a lot of people, this is very well known, but I mean, it's still a nice thing to learn. So this mimics the experiment. So, and this is really important. If you see a sharp frequency feature in the spectrum, right, in your spectrum that goes through the gas, and again, everything here is happening in time and then gets Fourier transformed at the end. If you see a sharp feature, you know that in time, that corresponds to a really long time scale, right? So if you have narrow absorption features in your gas, it has to somehow generate long time behavior in your fields that go through. And that's actually what happens. So if you look, for instance, in this calculation, here is in time the envelope of the input XUV field, and these are femtoseconds. So it really is about, I don't know how long it is, it might be 30 femtoseconds long. If you look at the envelope of the pulse that goes through the gas, it has this basic shape like the pulse we put in at the beginning. But the polarization that gets produced, which is out of phase with the driving field, makes this long tail. And so there's this long time feature that gets added to the electric field as it goes through the medium that gives you this sharp absorption feature. And it has to be that way because there are just Fourier transforms involved. And I'm not allowed to talk about photons or anything like that. Do you still give out Willis lamps?
He never gave me a license.
Right, so I don't know if you know this story. Willis Lamb, who was at the University of Arizona for many years, famously said that, you know, you never needed, or almost never needed to actually refer to photons to explain anything. And that if he felt that it was really, really necessary for somebody to discuss something in terms of photons, he would grant them a license to do so. He said he had about a half a dozen such licenses in his desk, and he couldn't remember the last time he gave one out.
Never got one.
Yeah, and Pierre never got one, so certainly I'm not getting one. So we have to do it this way. Right. And so what do you see? Again, there's no IR pulse. What do you see as you go through, right? Here's this pulse which is very broad in frequency compared to the resonance that we're looking at. So here's the XUV pulse before propagation. It's a short thing with a few cycles in it. And now we're going to have it propagate through the gas. And so what happens after it propagates through the gas is it gets this long tail dragging behind it. This long tail is oscillating at this 1s2p frequency, and it's out of phase with the stuff up here. And so at the frequencies that are in this tail, you're going to get destructive interference, and you're going to see less in the envelope. And these are actually seen, because this is a process that you can do at any time scale, right? You can do it with high-line Rydberg states and microwave pulses, so that this can end up on an oscilloscope, and they just see this. Now, we're going to work in the optical, and so we're not going to be able to see it on an oscilloscope per se, but this is, this is what's happening. So again, this is the idea that the input field went in and something got generated that's kind of out of phase with it. And so we had in frequency the input pulse, and in time it looked like this. And it goes to looking like something that has a sharp absorption feature in it and these temporal beats going through it. And this is an absolutely very, very generic picture of what happens when you put a broad pulse near a narrow resonance. And it was first understood at least as far back as Mossbauer spectroscopy around 1960, because it's very, very necessary. You know that in Mossbauer spectroscopy you have these really, really narrow absorption and emission features. And so any pulse in the world is broader than the Mossbauer spectral features. And so they had to understand this to understand what the lifetimes they were seeing were. And this is just a cute calculation. I don't really want to say much about it, but even in this sort of three-level system, if you add an IR pulse, you can get very, very interesting things. And this is based on the references on the next slide. Sorry about that. But this is based on the idea that you would have absorption going on, and when you turn on this IR laser, if it's resonant with this 2S state down here, then you can basically control the phase of the population that you're exciting, such that you can turn the system from absorbing to not absorbing. Now, it's not quite that simple, but that's basically the idea. And so, for instance, here we had a calculation where we put in a 60 femtosecond IR pulse that is resonant with this 1S2P thing. And so if we did the calculation without the IR pulse, what would come out would be just a greatly reduced envelope with this tail behind it. But what we do here is for the 11 femtoseconds right in the middle of the XUV pulse, we turn on an IR pulse that couples the 2P state to the 2S state. And that turns off the absorption in the system, or more directly, it modulates it. And it modulates it in such a way that it reshapes the generated field. And so what comes out is actually a shorter XUV pulse. It is just about 11 femtoseconds. So it's as if you have opened a transparency window for 11 femtoseconds right in the middle of the pulse. It's not actually quite that simple. It's actually, you really are controlling the phase, and you're cycling population around here. And one way you know that is that this 11 femtosecond thing that comes out of the gas is shifted by 4 femtoseconds. And that is actually the round trip time that it takes the amplitude. It's the Rabi flopping time. It takes the amplitude to go down here and come back up, because when it goes around once, it has the wrong phase, and it turns the...
So this is a version of EIT, right?
Thank you so much for saying this. No, Marlon Scully will now kill us both instead of just me.
You're on camera.
Why would you kill it by both?
Like he cares. It's not an interference effect in the sense that the EIT people talk. It's much better to think of it as an Altler-Towns effect, as an Altler-Towns splitting.
Okay.
So,
It sounded like EIT.
it is, it does, and it's been talked about that way, and then various quantum optics people, as Linda will tell you, get very, very upset. So, I mean, the reason that Linda knows all this is right, yeah, I mean, this is one of these things where people start yelling and it's not worth it. Right? And so, I mean, the idea was based on it. It's just a much cleaner version of an experiment that Linda Young did based on ideas that Robin Santra and Kristen Booth had. And they did this, they managed to very heroically make this work with an X-ray pulse, and so they had the X-ray pulse and they had a coupling laser, and they really were able to control the absorption. And I don't want to talk anything more about it, except to say that for me at least, this was a real inspiration, this experiment, to think about controlling polarization and absorption for meta as well. So now I want to get to talking about transient absorption and have the IR pulse there the whole time. So transient absorption, as we say, is a well-known technique for studying quantum dynamics because you can follow fast changes in the polarization by changing the delay. What you basically look at is the change in the spectrum, so you look at that differently. The usual case, the IR pumps the system and it starts the clock, but in this case, it's the XUV that's going to do it. There's no constraint on frequency, resolution versus delay, frequency versus delay, because delay is not time. In other words, we're looking at complete pulses going through with the spectrometer not distinguishing time, right? All you know is the frequency spectrum that came through. And you don't know at what time the processes happened, at least not a priori. So that's why the uncertainty principle doesn't take away. All schemes take advantage of the synchronicity between the XUV pulse and the mated. The first extension to the Attosecond domain was this experiment done in Ferenc Krause's lab in collaboration with Steve Leone and Dan Newmark, and that was very different than what I'm talking about. So this is a paper in Nature in 2010. Here the IR pulse really was the pump. It ionized the system and then they probed the system with the XUV. That's not what we were talking about. So we want to do the transient absorption in neutrals. So the XUV pulse is going to pump the system and start the clock. The XUV pulse too weak to excite the system. We'll look at the change in optical density. That's the fancy word for it. We'll look at the energy that gets taken out at each frequency as a function of the delay. Once excited, the electrons experience the IR field as strong. So there's fast ionization, strong couplings. And there's lots of experiments that have been done in these type systems now. This is an incomplete list of people that have been studying this experimentally. So this I talked about the other night. So the question is, in the picture we're using, absorption is a macroscopic phenomenon. I just said it's an interference phenomenon from the generated fields. Can I think of absorption at the single atom level? And the answer is yes. So I just want to go through this because it's kind of interesting to think about, can you do this? So at the single atom level, what can you think of, since I don't have photons and things? Well, at the single atom level, I can think about the energy that gets absorbed from the beam by the atom. In other words, I can keep track of how much energy has the atom absorbed, and I can relate that to the energy that must have been lost by the XUV pulse. And so I start with my standard Schrodinger equation, one electron, in a pseudopotential Schrodinger equation for linear polarization. It looks like this. Here's the field, here's Z. The plus sign is correct because this is not the dipole, it's the Z operator, and the charge is negative. So here's the thing. Here's what I'm going to use to do this. I'm going to say the energy that gets gained by the atom is going to be the integral over the whole pulse, so over all time, of the rate at which it gained energy. Who could argue with that, right? So now I can use the Feynman-Hellman theorem and the TDSE here to prove that the rate at which the energy changes, time derivative of the expectation value of the Hamiltonian, all the terms that involve d psi dt cancel out when you use the Schrodinger equation. All that's left is the partial derivative. In other words, does the Hamiltonian have an explicit dependent on time? Why, yes it does. That's in the electric field that's driving the whole system. Right? And so you end up with the rate at which you're gaining or losing energy is equal to the expectation value of the Z operator, so this is proportional to the dipole moment, times the rate at which the electric field is changing. Now, the expectation value of the Z operator is, I'll call that Z of t. The expectation, the dipole moment in the system is minus that because of the negative charge of the electron. So here is my expression for the energy gained by the atom over the whole pulse. And it's written here in terms of the Z coordinate at the time derivative of the electric field. You can transform this by using the integration by parts into something that involves velocities and the electric field or the acceleration and the interval of the electric field, whatever you like. It's all, so this is a, it doesn't look like it, but it is a gauge-independent number that will agree no matter how you calculate the wave function. And so now I want to define something. I want to define this capital lambda. It is the Fourier transform of the dipole moment that we get out of the whole calculation times the complex conjugate of the field that's driving it. So the tilde is here, that's always Fourier transforms. And so now, just by plugging the Fourier transforms of these things into my equation for the energy gain, I can now express the energy gain in the frequency domain. It's minus I times omega times this lambda of omega thing. And now I have a little bit of stuff that's just definitions. The dipole moment, d of t, and the electric field, E of t, those are real functions. So that constrains their Fourier transforms to have this symmetry. All right? They have to be odd functions. And so this lambda has that same thing. And so now we can take we can use these properties to re-express the energy gained over the whole pulse as 2 times omega times the imaginary part of this lambda function. So this is the energy gained by the atom over the whole pulse expressed in the frequency domain. And it comes from, mechanistically, I want you to understand, it comes from doing a calculation, single atom calculation, keeping track of the dipole moment for the whole pulse, Fourier transforming at the end, multiplying it by the Fourier transform of the driving field, complex conjugate, take the imaginary part, here's the energy that gets gained over the whole pulse. But now I've done something that I wanted to do. My original expression was just an integral over all time, so it's very opaque. But now I have the energy gain broken down into frequency components, right? So this begins to look like something like a cross-section, right? Because the energy gain looks like omega, you could think of that as h bar omega, right? Here's the energy gain times a probability for gaining, for being excited per unit frequency. So this starts to look kind of like a cross-section. And now there's just a few more steps. So this again is my expression for the energy gain. So this lambda, if I were to divide it by the flux of incoming radiation, this now looks like a generalized single atom susceptibility. It looks like something where the imaginary part corresponds to absorption or emission. And although I'm not going to use it in this talk, the real part of it corresponds to dispersion. It would tell you whether the light was traveling. It would tell you the extra little bit of phase that got added per unit frequency to the field by this interaction with this single electron, with this single atom system. So I'm not going to use that, but I just want to say that's kind of what it looks like. And the reason I say generalized is because the sign of this is not fixed. I could have absorption or emission, right? And I could have any kind of dispersion I want in principle. So what we do is we talk about the imaginary part of lambda. We talk about that as a single atom response function, this S of omega, and it depends on delay. That's what tau is. And looking at this, you can just read it off. It's 2 times the imaginary part of the dipole times the complex conjugate of the driving field. It is an absorption probability per unit frequency. And it's tied to the pulse that you're using, right? In other words, different pulses will make different d of omegas here. And so now this is kind of nice because we can write the total energy that gets absorbed by the atom as just the weighted integral over this response function. So I take S of omega, I multiply it by omega, I integrate over all positive frequencies, and I get this energy gain. This is these two things multiplied together are an even function of omega. So I mean, you could integrate over the whole spectrum and then just take out the factor of 2 there. But there's no need to. There's no new information at the negative part of the spectrum. A nice thing about this is you could say, at the single atom level, if I'm absorbing energy, that's because I got excited, right? So you could ask the question, at the end of the pulse, what is the probability to not be in the ground state anymore? And you can show that if you take this response function and integrate it over all frequency, it will give you the change in population. And this is an important check. You can do it from your You can check your calculations this way, and it really does work. So we've done something that we really wanted to do was we wanted to think about when the system gets excited and the IR pulse, moves population around. What is happening as a function of frequency? Right? And this response function really tells you that, but we calculate it from a time-dependent thing. Now here's a nice thing. You can go back, you say, well, how does this single atom picture match up with this interference picture in the gas that you gave me before? And the nice thing is that this interference term that we talked about before in the thin gas limit, this is exactly related to n, where that's the number of atoms, times omega over c times the single atom response function. So the single atom response function really is telling you the amount of energy absorbed or emitted per unit frequency per atom as you in the thin limit. So you can look at this either from a Maxwell point of view or from a single atom point of view scaled up. And this, of course, now allows people to yell at each other about things that don't matter. And you can get very interesting referee reports and stuff like that. Because some people feel like this is really fundamental and this is kind of accidental, and other people feel like this is really fundamental, and yeah, it goes to that. And this proves that my equations really are coupled in the way that I said they are. Right? This is good proof that the energy is going to disappear from one and show up in the other. And then, of course, if you want to have more layers of the gas, well, you really have to, worry about solving a couple of equations. So we have this frequency-dependent response, and it's an absorption probability per unit frequency. Dividing this by the flux of the incoming radiation, that gives you a generalized cross-section. Now, the incoming flux is proportional to the intensity, so the generalized cross-section is going to be omega times the imaginary part of this lambda function divided by the spectral intensity that you had sent in. In other words, this is how much energy do you have per unit frequency at a frequency omega. And this will, again, this is proportional to the E of omega squared. So when you take it's a real number, so you can take it inside the imaginary here, and it will cancel the E star, and so you just get this, which is a really standard, in chemistry, a really standard expression for the cross-section. The alpha here is the fine structure constant because I've done this in atomic units. If you want to do it in SI units, it comes out looking like this. But the point here is that because we have these two fields and we can redistribute the population all over the place, this sigma can be positive or negative. At any given frequency, energy could be added or subtracted because we can move it around, right? We're going to conserve overall energy, right? But we can do these sorts of processes. So this can be positive or negative, and it can include processes of many different orders, what Brett was calling photons, right? In this picture, a two-photon process is a second-order polarization process, right? 3 photons would be a third-order process. 1 photon would be a first-order process, right? So if you did everything in the frequency domain, you would have to write out expressions for each of those things. What's my first-order response? What's my second-order response? What's my third-order response? And, oh, the different frequencies are coupled, so your head would explode. But in the time domain, you just do the calculation, and then you Fourier transform at the end, and you get all the information. So this is always a nice thing about doing time-dependent calculations. So now let me look at some transient absorption things. So I just want to look at the single atom response and want to calculate that. One nice thing about the single atom response is because of the form of the function, where it's the dipole response times the driving field, if there's no driving field at a given frequency, then there's no response, right? And so I just get 0, and that's very good, right? The cross-section should also be 0, but that's trickier because the dipole response should be 0, and the field at the frequency should be 0, and those should give you 0. You never want to calculate 0, right, in a numerical calculation. You never want to try and calculate 0. It's right because you have to get everything exactly right. So you want to have something that's 0, you know, by itself if it's supposed to be 0. Okay. So that's why we think about the single atom response rather than the cross-section. You can go back and make it a cross-section afterwards. So here is a single atom spectrogram for one of these calculations. 800 nanometers, helium, EUV pulses, 330 attoseconds. It's centered up here near the ionization limit. It's very broad. The IR cycle is about 11, the IR pulse is about 11 femtoseconds long. And this is the spectrogram. So here's delay. Here I show you the IR pulse intensity envelope. So at a delay near 0, that means both pulses were there at the same time. Delays well away from 0 means the pulses arrived separately. And it really matters who came first, right? These things look very different. No, I want you to note on here that 0 is kind of this placid blue color in the middle. So the really dark blue guys here are emission, and the very red guys are a lot of absorption.
And this is helium.
This is helium. So here I have filtered out all of the stuff that's above 0, just to show you where the emission features are. These are frequencies where you actually get more out than you put in, because you have done a nonlinear frequency mixing process in the gas, right? You have used the gas as a nonlinear medium to do frequency mixing. And so that has subtracted energy from most of the frequencies, but added energy to some of the frequencies in a way that really depends on the delay between the two pulses. And there's lots of other stuff going on that I'll kind of talk about. So there's 3 regions here. If the IR pulse comes first and the XUV comes second, then you see just XUV absorption, because the IR did nothing to the system by definition. And you really see that. We just get the 2P, 3P, 4P, 5P. We just get those absorption features. The width here is just our artificial window. If you don't like how wide that is, we can do a slightly longer calculation and they'll get narrower. But they are just controlled by us. So that's completely checkable. Checkable word. In here, in this overlap region near 0 delay, this is really interesting because you get lots of new absorption features. And the bright state absorption features are greatly modified, and you get these new absorption features in between the bright states. We'll talk about that. So those basically, we call those light-induced states or light-induced structures, depending on what the referee wants you to say. Again, some people freak out when you say state, so then we call them structure. And then back here, this is the part of the spectrogram where the XUV pulse came first, pumped the system, and the IR came later. And you see this looks very different than either of the other 2 regions, right? Because what happens, this part is like the little movie I showed. The XUV comes along, it launches a wave packet by populating all the P states that are accessible. And then the IR pulse comes and moves it all around. And so you get funny absorption features. So here again is the XUV pulse comes in whenever it comes in, and it just populates every P state that it can. If I'm in the overlap region where the IR pulse is there at the same time as the XUV, then I see these extra absorption features, which you can think of as a second order process, right? First order out of the XUV pulse and either an emission or absorption process out of the IR pulse. And it ends up putting population in what is otherwise a dark state, right? If you just had the XUV pulse, you'd never get any population in the 2S state. But this process can put population there. And you actually see these light-induced features all over the spectrum because there's all sorts of second-order processes. So you can start to categorize these things by what is the bright state. So for most of the things we were looking at, the bright state that's populated is the 2P and also the 3P up here. And then the IR couples a bright state to a dark state, and it makes 2 light-induced states, one omega above the dark state and 1 omega below the dark state. That's sort of the thing. And so we can characterize these light-induced states in terms of the dark state that is being coupled to the light state in order to give you that feature. So we call this feature the 2s plus because it's one photon, one IR above the 2s state. Here's one below. This is in the approximation that the 2s and the 2p are really close in energy. Yes?
So 2s plus and 2s minus real state. I mean, is there actual state here? Or you go and come back to 2s?
So at the end of the pulse, the population, there's some population in the 2p state and some population in the 2s state. But you see the absorption feature here and here, right? So you can think of this as like a phase coherent Raman process where you take one photon out of the XUV beam and you either emit or absorb a photon from the IR beam, right? But whenever you absorb an XUV photon, you're going to see an absorption feature at that frequency. And so that's why it shows up here.
Ken, this all started, 3 minutes ago as you're showing us the emission features, not the absorption features.
Well, now I'm talking about the absorption. I'm just talking about where is there an absorption or an emission.
Okay, so this has not explained where the extra emission line was.
Yes, that's true. But to some extent, I'm not going to explain that. In other words, it's just the complicated dynamics can give you one or the other. And in any given model system, you can work it out by hand and show what form it should have. Right?
Well,
And this is, and by the way, this is very old stuff. Malo and those guys did this in the microwave machine in the early 70s.
so would it be crazy just to call them hyperamons? Could you populate 2s now? I can get hyperamons, I can get emissions.
It's okay as long as they really exist only in the overlap region, which is sort of how I want to think about it here. But it's possible to actually have it extend into the non-overlap region somewhat, in which case it's kind of hard to think of it that way. So I shy away from that a little bit. But it is a sort of a phase coherent hyper-Raman process. I mean, right, a regular Raman process would not give you the striping features that you see. So, and these extra features, by the way, these have been seen experimentally by several different groups. So here, for instance, is a comparison of our theory in this. Here's the 2p line, the 3p, the 4p. Here are these extra features that show up near zero delay. Here's an experiment done in Berkeley in helium, where again you have the bright state feature, you have these light-induced state features. When you turn the intensity down, these features get much less bright. That happens in the experiment as well. They do this experiment much, much better now, but I like to show this early thing because this was sort of how the collaboration with Leone and Dumark's group got done, because I gave a talk where I showed this and Steve said, "We have those. Is that what those are?"
And this is all the single atom response.
This is the single atom response, that's right. But these features can't get made by propagation. So in other words, they have to start at the single atom level and kind of go forward. But the exact form of them would depend on the gas density and how long the gas is and all that sort of thing.
And the main features agree with the experiment.
That's right, because they're doing this at low density and stuff like that. I mean, they're trying to make it. So unlike the generation and absorption, you really can go to the low absorption limit. It's just how hard do you want to work in the experiment. There's nothing sort of in principle stopping you there.
Why in the experiment they didn't see this oscillation?
Why in the experiment what?
They didn't see the oscillation. Because in the theory they have this oscillation.
Because the laser that they're using, the XUV pulse that they're using is not, the IR laser that they're using is not CEP phase stabilized, so it's jumping around all over the place. So in the experiment, they have integrated the delays over a small, like 2 femtosecond bin. So there are other experiments been done in Sang-Hu Chang's group. Oh, I don't have that slide, I'm sorry, but where they see this beautiful striping. There's nothing. So, and you can also see 3 photon processes where This happens in the regime where the two pulses are separated, where the XUV comes in, it makes a wave packet, it puts population in all the various P states. And when the IR pulse comes later, it can also move population, for instance, from the 2P state, where a lot of it is. It can move by a second order process, by a two-photon process. It can move an interference pattern, because the polarization that you observe at this frequency, right, that leads to absorption, it now had two possible ways to make it. This polarization could have gotten started when the XUV pulse was there and directly populated, say, the 5P state, or this polarization could start at a delay tau later when population that was initially in the 2P state got promoted to the 5P state. So you have two ways to make the polarization. You don't know which one, and as I always tell my students, whenever there's something you don't know, then interference fringes appear, right? Because there's this uncertainty principle, right? I mean, beautiful experiments have been done to show that there's a real trade-off between visibility of fringes and the amount of knowledge that you have. And here the knowledge is none, and so the fringes are beautifully clear. And you can show that the occurrence of these fringes is linked to the fact that there's a precise phase accumulation between these two events, between populating the 5P initially or populating at a later time. And so the appearance of these fringes and where they sit, actually you can back out of that, and in the paper we wrote it's done, that actually this second order process, this two-photon process, is happening at one of the peaks of the IR field. You can show that if it was happening just sort of randomly, then we again wouldn't get these nice interference fringes, because we would be integrating over more time than that. Oh, I don't have that slide, but also there's an intermediate process here that helps this two-photon process go on. There's like a 3S state that sits in here, and it helps this process go. And this one photon absorption that then leads to the second photon being absorbed, this can also add an extra phase. And it depends, this extra phase, of course, depends on whether the first photon brings you below the resonance or above it. You'll get a pi phase shift. A pi phase shift in the delay spectrum is equivalent to a quarter cycle shift. And so when we change the IR wavelength such that the first photon, instead of being below the dark state, is above it, we see this whole pattern shift by just a quarter of a cycle. So you can do all sorts of nice things like that. Okay. The IR coupling that leads to these sidebands, you don't have to think about it in much more detail than sort of a 3-level or even just a 2-level model. And so where you're in the ground state, some population gets put in a bright state, and then the IR couples you to that. And you basically, what you can work out is that the single atom response around the bright state is given basically by the real part of the Fourier transform of the amplitude, of the time-dependent amplitude to be in this state. So it really is that we're putting some amplitude in the bright state and then we're messing around with it. And that leads to a complicated behavior for the amplitude to be in that bright state, and that's what gives rise to the absorption. So let's just look at the feature that's around the bright state, this 2P state. And in this case, I have the 2P state, I have an IR photon spacing here, and the 2S state is far away from the 2P state. So in other words, this transition is detuned. And now I want to look at how this absorption, this response, changes as a function of the detuning. So I'm just going to artificially move the 2S state around and see what this response function looks like. And it's really changes a lot depending. So it goes from where, now I have to push the right button. When I'm far detuned, I'm going to make it go a little bit more than that. When the two states are degenerate, then the photon, the transition is very, very far detuned. And I get what look, these things that I've been calling light-induced states. if I change the detuning such that I'm almost in resonance, I get something that looks like an Adler-Towns splitting. And in this case, I can actually see how the Adler-Towns spectral modification happens. It happens by taking the population and cycling it around from the 2p state to the 2s and back and around and again and again and again. Every time you go around, you get a new feature coming out, right? And so I don't have time to go through this in detail, but you can really, if you can measure one of these things, you can really see how the Adler-Towns feature builds up in time. If you're detuned, you get these light-induced states. So there's no real fundamental difference between seeing the light-induced states or seeing an Adler-Towns feature. It just has to do with the detuning between the bright and the dark state that are being coupled. Yes?
What are the colors telling you?
The amount of stuff. So the red is a lot of absorption, and this is a little bit of absorption. And the really dark, there's some really dark blue along here, which is emission. And I just want to say, we talked about the response function. If I were to integrate this over all frequency at every delay, I would get the same answer at every delay. Okay. Because I'm just putting a certain amount of population there, right? So the total energy absorption is not changing as a function of delay, because I have just one pulse, one XUV pulse, one IR pulse. But I'm moving it all around. You can think of this in a flow K picture. I don't, unfortunately, have time for that. I want to kind of leave some time for Paul to talk. It's very interesting. You could ask me about it. But I want to just highlight a very cool experiment that was done by Giuseppe Sansoni's group in Milan a couple of years ago, where we tried to look at, well, what is the physical reality of these light-induced states? I mean, do we really understand what bright and what dark state are being coupled together, right? Because the dark states are never seen explicitly, right? What you see are these light-induced states, which are the fingerprint, if you will, right, in the spectrogram of this coupling, but you don't have that state exactly. So here's what they did. In helium, again, we had talked about that you have the 2p state, 1s2p is a bright state, and we talked about that the IR laser could couple you to the 2s state and give you a feature that you might call 2s minus, or a feature up here that you might call 2s plus. The 3p state could also couple to, the 2p could also couple to the 3D dark state, give you light-induced features that you would call 3D plus and 3D minus. And so you would expect to see, for instance, these 2s plus and 2s minus features and the 3D plus and 3D minus features if both the IR and the XUV, the polarizations are in the same direction. Now, what happens if you turn the polarization of the XUV field? Then what happens here is that if the two polarizations are parallel, then the IR field is able to take the population that you excited to the 2p, m equals 0, and couple it to the 2s. And couple the 3p to the, couple the 2p to the 3d and make these light-induced features. But if you turn the polarization by 90 degrees, now you have population in the 2p m equal plus 1 or minus 1 states, and the IR laser cannot couple that to the 2s state, which is m equals 0. So that light-induced state should go away. Now the 3D states, there are ways to do this coupling with m equals 0 or m equal 1 or m equal 2, so some of that should survive. And so they did this experiment. So here's the theory first. The spectrogram for the aligned pulses looks like this. So look at this area. And as I rotate the polarization, the 2s plus feature goes away. The 3D minus feature stays. Here's the experiment. It's, again, the CE phase is not locked. A lot of things. But you see these light-induced states, light-induced features in here. There's a 2s1 and a 3d1. And as they rotate the polarization, they really see these features go away, and it really cleans up what happens here. should see that again. So you're seeing these light-induced features. We're predicting some of them go away and some of them stay. And that really does happen. So that was very nice. We also do full dimensional calculations in helium. This has been a big deal over the last couple of years. Thomas Pfeiffer's group has been doing transient absorption near the autoionizing resonances in helium. So we've been doing full calculations using a code that was written by Schaffer, who's a member of our group. And all I want to highlight here is that this is above threshold in helium. It's near 60 eV, where you have a bunch of autoionizing resonances, which are basically just doubly excited states that live for a while and then fall apart. And you see all the same sort of things. You see modification of here's a bright state, because it's basically what you would call the 2p, 2s, 2p doubly excited state, and couples to some dipole not allowed, so some dark doubly excited states to give you modification of the absorption features. It's better to actually plot this spectrogram taking the different regions of it and rescaling the axis so that you can see that actually in this absorption spectrogram there's actually many, many different features that look exactly like we were seeing at the single atom. There's modification of the bright state line. There's a lot of light-induced states. I want to talk about just one of them. There's two states right around 60 eV that get strongly coupled by the field, and they're essentially degenerate. So they make a light-induced state that is above and below. And what I want to, so you know that there's a bright state and a dark state that give rise to this coupling. And you can ask yourself now, well, what about that dark state? What do we know about it? And the answer is very little, because it's not seen in spectroscopy. The only way to see it previous to this would be to turn on a very strong electric field and try and break the rotational symmetry, and so make these previously unallowed transitions allowed. The IR laser here puts an electric field on that's 50,000 times larger than anything they've ever done, right? So you really see the signature of this dark state. Well, what can you learn from this? Well, actually, you could try and look at this light-induced state sideband. You can pass it through a low-pass filters to get rid of these fringes. You see this light-induced feature. One thing you learn right away is it has the same dispersive phono line shape as the bright state had. So that's kind of an interesting thing to learn. You could also learn a prosaic thing, which is you could ask yourself, what is the IR matrix? What's the IR coupling between this bright state and this dark state, which are both doubly excited resonances? You cannot go to a textbook and just grab those wave functions. Those are not bound states, right? It's really hard to make, and it's really hard to figure out what is the dipole matrix element between those two states. But you can pull that out of, if you look at the amplitude of the 2 omega fringes here, and I haven't talked about where they come from, and I won't have time. But the point is, you can prove that the amplitude of these 2 omega fringes is proportional to a whole bunch of stuff that you know, times the matrix element that you don't know squared. And so when we do that, we can pull out, from just looking at the spectrogram, we can pull out that the matrix element is 1.9 atomic units. I would say very close to the 1.7 that we laboriously calculated from calculating resonant states. So that's a kind of a use for that. I want to just quickly say something. Our postdoc, Mengshi Wu, likes to think about this as a signal processing problem. So I promised him I would say a few words about that. Basically, there's a little comment here which we can look at later. This either. But you can basically say, let's say I'm looking at a spectrogram like this and I have some feature and I think it's due to a light-induced state. I can try and cook up some theory and then say, does my theory match that like I was doing before? But the signal processing way to handle this would be to say, I'm going to calculate a whole bunch of different spectrograms, assuming a whole bunch of different dark states that are somewhere. And then I'm going to sort through the catalog of spectrograms that I calculated and see, can I pull out information about the dark state? And the short answer to that is yes, you can. You do it by what the signal processing people call calculating the correlation. This is almost like the convolution, except it's not. The convolution would be a minus sign here, it's a plus. But this is a way to pull out, does a signal, an actual physical signal, exist within a noisy background? And I just want to say that, so what Mengshi did was calculate a whole bunch of different spectrograms and then compare them via this correlation to the actual spectrogram. Here is, this index just shows you the index of all the possible spectrograms. And this correlation, the way that we've done it, when it matches really well, you get a minimum. And I just want to say that the two minima, the minima that we get here and here, correspond to the correct position of these two dark states that we didn't otherwise know. And this is, again, for a student, you always want to learn techniques, right? You always want to learn, if you can learn signal processing, just like 10 and 15 years ago, a lot of people in physics and chemistry learned a whole lot about neural networks and learning algorithms because they were thinking about quantum control. And I'm sure that turned out to be really useful to a lot of people, even if they didn't stay in physics but went on. And so this signal processing aspect would be very interesting. Now I'm really done.
Thank you, Ken. This was another beautiful lecture. Let's see who wants to ask a question.
Ken, when you were talking about the helium absorption as a function of detuning, you made the comment that if you integrate everything at each detuning, you get the same result. And my question is, if you're on resonance, will you absorb more than if you're detuned from resonance?
The XUV pulse is very broad and it doesn't change. And so you're always absorbing the same amount of energy from the XUV pulse. Right? So in other words, the absorption process, the amount of population that gets put in that bright state is independent of delay. And then you're just rearranging things.
It's just a rearrangement.
That's right. That's right. And so, you know, this is, you know, early on when we were on sabbatical in Stanford, and I think we went and talked to Phil and David Reese about this, they went, eh. and that was, and that was a good clue, right? That there's a way of thinking about this where it looks really head-scratching, and there's another way of thinking about this where it's not head-scratching at all. And I would say that this is kind of the hallmark of ultra-fast physics, that you're always kind of jumping around between pictures where things look complicated or things look eh, right? And not to say that you can't learn something. Right? Okay.
Yeah.
If in this case you just rearrange this frequency, I mean in the histogram on the very right side, you will only have this absorption. I mean on the very right side.
Here.
Yeah, yes.
Yeah.
You only have absorption, but there's a low ET.
So the color scale is saturated. So here you only have absorption. It's a lot. In other words, this would really go. If I made the top of this peak visible, then it would be very hard to see all of this, right? Because I've taken this whole line and spread it out all over the place. So I've had to. I mean, my color scale is saturated. Is the short answer to that. So when I said you get the same answer integrated overall frequency every time, I didn't stipulate that, you know, it might go out the top of the plot.
More questions? Comments? Criticism?
Sure.
Okay. Here, I'm wondering what kind of wave function do you use here? You use the bounces, you use bounces to the calculation, or you?
So we do the calculation a lot of different ways. We use bound state wave functions. We do the same numerical calculation that we always do. You get the same answer each way. In other words, the nice thing about it is that the different features that show up in the spectrogram are due to specific strong couplings that observe. So you can kind of, even though the spectrogram looks very complicated, and you can calculate it with a lot of different states in there, You can also take the features apart into, you know, what coupling is causing this and what coupling is causing that. So once you know what's going on, you can calculate some of the things really simply, just using some bound state wave functions. But before you know what's going on, you can calculate the whole thing just using a numerical wave function that includes ionization and all sorts of things.
Because here you use this field is very strong. So do you also include the start effect? You have
Yes.
strong electric field.
Yeah. Yeah. Because, for instance, down here near the 2p state, the entire what you think of as the Stark effect is almost exhausted just by the coupling to the 2s and the 3s. That's actually what makes the Stark shift. Whereas if you have the higher lying states, the Stark shift, you have to integrate over a lot of things, and then you get the fundamental shift. So in the full calculation, we have all the Stark shifts and everything. They're all in